All right, so I have a strong feeling I'm live. So please just comment in here if you can hear me, that'd be wonderful. All right, so today's live stream is on limits, continuity, and differentiability. So remember, just as usual, comment if you can hear me, that'd be wonderful. So, limits, continuity, and differentiability. Really core ideas in how differentiation works. And I know that we've experienced differentiation in level 2, but I kind of wanted to go over it in a greater detail in level 1. Perfect. Thanks, guys. This is outstanding. So let's talk about what differentiation is. So differentiation is the study of change, how things change, right? And so the key area of change that we've looked at so far is gradients. So gradients of functions become very key areas of change. Hi Caleb, hi Oliver, hi Kate, hi Jackson, hi Harry. Hello Mr. This is outstanding. Oh, hey Jason up the top. So gradients are the fundamental part of what we've done. And in differentiation, we looked at gradients and we looked at change. And then in level 2, we did a few differentiation techniques, but I think there's a lot we're missing. And so before we come and do any of this stuff, I want to cover ideas on limits and what functions approach. So here are some little, that's not what I want happening. Hold up. Okay, let's try this. Limits. Limits are an idea of what you expect functions to do. Okay, and that's how simply I'm going to define this. What you expect functions to do. Okay, so let's have a look at a few examples. I'm going to pull up a function and insert an image. Of a nice graph. This function is one of my favorite functions ever. F of x equals x. Fairly comfortable function. I want to ask a question. Question 1. What is f of 1? Question 2. What is f of negative 1? And question 3. What is f of 2? Right? I felt my pen was getting a bit thick there, so oh well. Can you tell me what these are? Without too much stress, all of you should be able to tell me, well, f of 1 is 1, f of 2, no, f of negative 1 is negative 1, and f of 2 is 2. 1, negative 1, and 2. So that's not really a challenge, is it? So what if I said, are all functions this nice? No, if I shift it, the function will change a little bit. But I'm going to ask, what is f of 5? 5. Now, I'm going to use some new notation. This notation is called limit notation. Alright? What is the limit as x heads towards 4 of f of x. Can you tell me what you think that means? As x gets closer to 4, what does f of x get close to? It's 4 there. Well, if you notice, as I get closer and closer along this value, as I get closer and closer to 4, y, or f of x, looks like it's getting closer and closer to 4. But if I do the same thing from this side, I'm getting a value that's almost exactly 4. Actually, it's exactly 4. So I can say the limit, thank you, Oliver, the limit as x tends to 4 on f of x is 4. Okay, cool. You're like, okay, Mr. Dharma, no surprises there. What's really exciting? Well, sometimes you have functions that you might need a limit for. So here's a function. I want you to tell me f of x equals what is, for this function, just the same, what's f of 1? What's f of 3? What's f of negative 1? Can you tell me? Okay, so I'm not hearing anything from you, but I'm assuming you're all plugging in and seeing. So let me plug in some numbers. So let's do f of 1. 1, 1 minus 2 over 1 minus 2. They would be the same. Okay, Oliver, there we go. So that's negative 1, that's negative 1. So that's negative 1 divided by negative 1, that's 1. Okay, cool. Let's do 3. 3 minus 2 over 3 minus 2. In fact, the 3 minus 2 cancel. Oh, oh. Okay, I see what you're saying. And so I don't even need to do it. That just happens. They cancel. Okay. If y'all are that comfortable, what is f of 2? What happens when I plug in f of 2? Well, check this. 2, 2 minus 2 over 2 minus 2. Are you... Ooh, boy. Where'd you go? Are we comfortable with this idea? This is 2 times 0. Well, someone said we could just, sorry, I'm just going to change. Someone said we could cancel that 0 and that 0 out and just get 2. Okay, would that be okay? Or should I go, well, 2 times 0 over 0, and 2 times 0 is 0, and 0 is 0. 0 divided by 0, what's that? Which of these is correct? And yes, those of you getting math error, you're correct. Because if you do this on your calculator, the whole idea of dividing by 0 is terrible. So the idea of dividing by 0 is outrageous. And so even though for every other point f of x seems to be x, it's not, because when x equals 2, something crazy happens. And so you're like, okay, Mr. Dharma, surely if I plotted all of this, this looks exactly the same. And I'm going to show you what the graph of this looks like. And so the graph of this has a really unique, interesting way of being. Look at this. For all intents and purposes, it's the same as y equals x, but there is a hole here. And this hole is where x is undefined. Okay? Because if I can't plug in the x value into the equation, then it's undefined at that point. So essentially, this function is y equals x with a hole in it. You could say it's holy, right? So when x equals 2, this function is not defined, but it's defined for every other function except when x equals 2. And so this point here is called a discontinuity. Better spell this right. Discontinuity. It's because it's where the function stops existing. And for those of you who suggested we should just cancel the x minus 2, that's not okay, because you can't do that if the denominator is a 0. And this is where a function becomes slightly different to what you expect it to be. Okay? So let's quickly write something. You can see we know f of 2 is undefined. However, limit as x tends to 2 of f of x is equal to what? As we get closer to 2 along the x-axis, as we get closer to 2, we're getting closer and closer to, what's the y value we're getting closer and closer to? The y value we're getting closer and closer to is 2. So, f of x, sorry, f of 2 is undefined. But the limit as x tends to 2 of f of x is equal to 2. So the limit is what you expect it to be, right? Because you expected it to be 2, just like your other function. But what it actually is undefined. And so now we have an idea of what a limit is. It's what we expect it to be. Yes, Eddie, thank you. It's what we expect it to be. The function is undefined, but the limit exists. Because from this way and this way, we expect it to be the same number. And that's how limits work. We're looking at what a function is going to be. Now, before we carry on, let me give you another function. F of x equals x minus 2, x minus 3 over x minus 2, x minus 3. Can you tell me what you think this function will look like? Will it be f of x? Try to draw this. Yep, thank you, Eddie. Yep. This function seems to be the same as f of x, but I really tried there to get a straight line. I am really not going to try anymore. Okay, you've got this, but when x equals 2, there's a gap. When x equals 3, there's a gap. And what we're going to do is we're going to put a little circle and we're going to see, okay, I know it's not to scale. Yes. Exactly, Jason, yeah. So we say this function is discontinuous at x equals 2, x equals 3. But what else do we know? We know that for this f of x, as x tends to 2 of f of x, limit of f of x is equal to 2, and the limit of x tends to 3 of f of x is 3. So the limits exist, and these are defined such way, but the function is discontinuous, and f of 2 and f of 3 are undefined. So, okay, are we almost done? No. So that's limits and that's continuity. That's discontinuous. Where you see a gap. Now I'm going to present to you a couple more scenarios and I want you to talk to me about what's happening. And then we'll formalize some notes in some way. Okay, so I'm going to give you another picture and I want you to tell me what happens at f of x equals, or f of x. Tell me what f of x might imply. Okay, here's a function. look at this function. Tell me, what is f of x? Okay, no. Let's go read. For question 1, what is f of 5? What is f of 5? Question 2. What is f of 0? Question 3. What is f of 1? And then question 4. What is f of 2? And then question 5. What is the limit as x tends to of f of x? Alright. Let's have a look. What is the function defined as? So at 5, it's 6. What about 0? It's 0. And at 1, it's 1. What of f of 2? Well, at f of 2, the function, since this dot is colored in down here, it is defined as 2. But the limit is what happens as I get closer and closer to 2. And from this side, it's getting to 2. And from this side, it's getting closer and closer to 3. And since those two numbers are not the same, we say does not exist. So here the function exists, but the limit doesn't exist. And that's kind of wild, because the limit, for the limit to exist, it has to be the same value from both sides. And so what I want to do is I want to draw a rough picture of the 4 cases. Okay. Okay. I'm not an artist, but here we go. So we're going to talk about the limit here and the function here. Okay. So the function is either defined at a point or undefined at a point. It either exists, the limit either exists or does not exist. Okay, those are the 4 scenarios that we can get. All right, so let's have a look and draw a picture of a function where it's defined and exists. So I have a blue line. And so if I want this here, at A, the function is defined and exists. all right, is defined and the limit exists, right? What about where the function is undefined but the limit exists? Well, that's our second example. So once again at A, our function is undefined, but our limit exists. What about where the function is defined, but the limit doesn't exist? Well, that's another one that we can do. This is A. It's got a full circle here, but a half a circle up here. You could copy this down, or you could watch this back later and copy it down. Um, um, it's the idea building. You could probably get notes later on, Jason, but I think it's pretty cool to copy down. I think it's really important, like kind of a very important idea. Um, functions, limits, and their existence. Okay, and so we're almost done. Now let's look at a function that is undefined at a point, and the limit doesn't exist at that point. Well, draw this. Draw my A, and I'm going to draw a hole here, and I'm going to draw a hole here. And so there's no colored in blue bit, and so it's not defined. If there's a colored in blue bit, then it's defined. But the existence solely depends on if that colored in blue bit, if that hole was filled in, would it be the same point for both of them? And this diagram is my limit function diagram. These are the four cases for limits. Is f of x defined? Does the limit exist? And this is how I would tell. Okay. Okay. So let me show you one more situation, and then we're going to talk about another thing. All right. So have a look at this graph here. I'm really trying to move it, guys. It's just not playing ball. Nope, that's not what I wanted to do. Nope. All right, I'm just going to work with it here. Whatever. So tell me, what is f of 1? What is f of 5? And then 3, what is f of 2? And 4, what is the limit as x tends to 2 of f of x? Okay, and so in this one, it's really interesting. F of 1 shouldn't be, it's not a trick question. F of 1 is 1. F of 5 is 2. F of 2 is also 2. And f of 4, the function, what is the limit? Well, from this side, it's getting closer and closer to 2 in the height. And from this side, it's getting closer and closer to 2 from height. And so it's 2. The limit exists. Okay, so even though it looks funky, the limit still exists. because the limit only exists if it approaches different values. The limit only doesn't exist if it approaches different values. Otherwise, the limit's fine. And if there's a circle coloured in one place somewhere else, then it doesn't matter. It's only what do we expect it to be? That's what a limit is. Okay. Now, so let's define a few things and then see if we've covered everything we needed to cover today. So limits. Where we expect functions to go through. Okay. Second, can either exist or not exists only when they go to the same value from both sides. So, once again, really, this has a limit. What is f of x for that graph? For this one, Harry. So for this one, f of x is a piecewise graph. It's f of x is equal to x for x less than 2 and f of x equals 2 for x greater than 2. Right? So that's how I'd define that function. But that's what limits are, right? So they either exist or they don't. They only exist when they go through the same value. Okay. Now continuity. Continuity is another cool idea. Yo. Function is continuous at point if the limit and the function have the same value. So that is to say, if f of a equals limit as x tends to a of f of x, then f of x is continuous at f of right, that seems a little crazy. But what I'm saying is, if I can draw it without taking my pen off the paper, then it's continuous. If I can draw it without taking the pen off the paper, it's continuous. Wherever I have to take the pen off the paper, it's discontinuous. If I have to take the pen off the paper, it's discontinuous. So we have continuity, so this is continuous. Hello, that was the wrong color. So this is continuous, right? And the limit is defined for all of those points, and it's kind of nice, right? But if I stuck a hole in it, now it becomes discontinuous at that point, right? But now there's one thing I've not talked about. I've talked about limits, I've talked about continuity. I haven't talked about oh my days. Differentiability. Okay, that's only because we haven't talked about what differentiation is. But differentiability is I'm going to change this to blue. Can you find a gradient? That's it. Can you find a gradient at that point? At that point, can you find a gradient? And you're like, Mr. Tama, that's the weirdest question you've ever asked. And I'm like, no, it's not. So let's import all these pictures again and see what that means really quickly. Okay, let's look at all of these 4 pictures, right? There's this one, there's this one, not playing ball today, computer. Right, sorry guys, I'm really trying. I don't know what my computer thinks is wrong. It just won't do it. Alright, so anyway, I'm going to go back to the pictures up here because that's annoying. Okay, so here we go. So here, every point on here, I can find the gradient. It's nice and smooth. Okay, so that function is always differentiable. This function here, it's got a hole in it. I can't find the gradient at that point because it's not defined at that point. So, not differentiable. So if it's not continuous, it's not differentiable. Here, it's not continuous. It's got a gap in it. So, it's not differentiable everywhere. So the function is not differentiable at this point. And so if it's discontinuous, it's probably if it's discontinuous, it's not differentiable. And then come back to here. If it's got a sharp turn in any way, it's also not differentiable. And the reason for that is is because it needs to be able to be differentiated smoothly. If I were to stick a ruler on here, and you're like, oh god, Mr. Dharma, good luck. You can sort of see the slope here is about, what should be 45 degrees, right? So it's got a gradient. And the slope here is 0 degrees. And you're like, oh, that's really cool, Mr. Dharma. Wow. But at that one point, there is no fixed slope. Because how do you get from 45 degrees to 0 degrees without doing anything? And you can't. So the gradient changes really quickly. And the slope changes really quickly. And because of that, it's called a not differentiable point. So a function is only differentiable if it is fully continuous, if it's continuous at that point, and it's got no sharp turns at that point. I'm going to try and delete these now because these are just annoying me now. And I'll just draw my own. So the function is differentiable at a point if it is continuous and smooth. What I mean is has no sharp turns. Okay, so it can't look like this. That's not differentiable. Okay, so a function has limits. So the limits are what you expect it to be. The function has continuity if there's no holes, and a function has differentiability. It is differentiable if it's continuous and doesn't have sharp peaks like this. Right? Because at this point it's too hard to find the gradient. And that is the three ideas here. Is it continuous? Is it differentiable? Does it have a limit? Okay, now there's some exercises in your book that you can do. How do you work these out? Well, if you've got questions like this, limit as x tends to 5 of x squared, x minus 5 over x minus 5, right? This function, this f of x, if I plug in 5, I get 0 equals 0. But fortunately, with limit algebra, we're not ever equaling 0. So I can cancel these out. And so then I go, as long as I keep this limit out the front, I can write this. And now, what is 5 squared of x was equal to x squared x minus 5 over x minus 5. F of 5 is undefined. Ain't that a crazy? Whereas limit as x tends to 5 of f of x equals 25. That is wild maths. And this function is not continuous because it has a hole at 5, and it's not differentiable because it has a hole at 5. Okay, I think that's enough for today. If you have any questions, please sound off now. I'll look at answering them, and then I'll just call it a day. And there's some pages in your book that your teacher will have shown you that you can do. All right. Any questions, guys? If not, I'm going to end the stream now. Perfect.